Hey everybody, welcome to today's lecture for mobile computing. This lecture is lecture 4 and it's entitled How Java Handles Memory. As usual, we're going to start off with something like, why are you listening to me? What possible reason could you have to listen to me? Well, this lecture covers how Java handles memory, as stated before. Now, in C++, you had control over memory, right? So you explicitly created and destroyed objects using the new operator and the destroy operator, and you had malloc and free. I'm not sure if you guys use those, but you have those capabilities to manually deal with memory, and you could manipulate pointers. So you guys probably learned all about pointers, and you could do all sorts of cool things with them. Now, you probably had some problems with pointers in first year for a while. You may completely have the hang of it by now, but it's not the most straightforward concept. And one of the problems with it not being straightforward is that often that means people make a lot of errors using pointers, right? So with Java, the design is such that basically the idea is you don't have control over this anymore. Java will handle memory management for you. It'll handle pointers. It'll take care of it for you. The problem with this is that whenever something is handled for you, it's possible that it's going to be handled in ways you don't like, right? It's possible that it's going to be handled in ways that are unpredictable to you. So whenever something's handled for you, it's worth figuring out how, it's worth checking how, so that when something odd happens when you're coding, you know why it happened, right? And how to potentially fix it. But before we start, we first have a logic puzzle. So today's logic puzzle is the first of a set of puzzles we call hat problems, and you're going to get a lot of those hat problems in this course. They're quite cool logic puzzles generally, and they have a sort of similar framework. How they work generally is you've got some people, and then you've got some guy who puts hats of different colors on their heads, and then they can't see their own hats, but they can potentially see other people's hats. In today's particular problem, there's 3 men standing in a line, right? So picture there's 3 men A, B, C, and they're standing in a straight line. So man A, who's at the front, can see no one, right? Man B, who's in the middle, can see man A, and man C, who's at the back, can see man B and man A. Now, no man can see his own hat. So basically, the guy in the front, man A, he can't see anything. Okay, man B, who's the guy in the middle, he knows the person in front of him's hat. He knows A's hat. And man C, who's right at the back, can see both A and B's hats, right? Now, so they're put to sit like this in a line. And then the man running the show, the person who puts the hats on their heads, puts either a black hat or a white hat on each person's head. And he tells them that he chose this from a set of 3 white hats and 2 black hats, right? So there was a set that was 3 white hats and 2 black hats. And then he randomly chose hats to put on people's heads, okay? Then he says, look, there's 3 of you. If any one of you can guess your own hat color, you guys win, and I lose, okay? And then he says, okay, go for it. Let's see what you got. Now, the men sit and think about this, and after a while, the guy in the front, the guy who can see nothing, he guesses his own hat color. He guesses it correctly. So it's not actually a guess, right? He figures out his own hat color. So the question I want to ask you is, what is his hat color, and how does he know? Okay, so I want you to think about that. Okay, you can possibly pause the video and think about it, but yeah, if at any point you have a solution, I'd love to hear it on Discord. Again, you can obviously Google it and cheat and stuff, but that's not particularly fun, right? So yeah, give it some thought, see where you get. And now back to work. Okay, so we were talking about memory management. So let's say we've got the following main method, the one that's sitting there on the right. Int age equals 5, system.out.println age. It's a pretty straightforward program, right? It's in a class called lecture 3, and it's the main method. Now, what Java will do is, I don't know if you remember from C++, but you had the stack and the heap. Now, in Java, you've got a similar structure. You've got a stack and a heap, and whenever you call a method, in this case, the main method, Java will allocate a stack frame, right? So you get a stack frame for every method that you call. Then primitive variables, Those are the sorts of variables we talked about in the last lecture, like integers and booleans and chars and bytes and longs and floats and doubles. Basically variable types that start with a small letter are allocated directly in the stack, right? So in the stack frame for the method that they're local to, they'll be allocated. But objects, meaning variables of a complex type, like strings and scanners, and I'm not sure what other objects you guys have seen. Let's say strings. Let's just leave it as strings and scanners for now. When you create those using the new operator, those objects are stored on the heap. And what goes in the stack frame is just a pointer to that object. Okay. That may not have been completely clear, but we're going to do some examples now, so it'll hopefully become a bit more clear. Okay, so we've got this these blocks which represent our stack and our heap. In executing this bit of code, what happens is that we create a stack frame for main, right? So here's our stack frame for main, and we have a local variable age whose value is 5. Okay, so then when we call system.out.println on age, the value is 5. Okay, if we had another variable int other equals 15, we'd just have another variable inside the stack frame, right? Inside main's stack frame. So we've got other and 15, and if we system.out.println other, we'd get 15. So far that shouldn't be in any way confusing, and everything should be quite predictable there. Let's look at what happens when we do a function call. Okay, in Java we call them methods, so we'll have a method call. So what we're doing first is we're creating a method called change. Okay, this is our change method, and it's void. That means it doesn't return anything, and it takes in a variable called age. Okay, so that means we send in a variable called age, and what we do is we set the value of age to 9 when we receive the variable. Okay, so when we're executing the main method, Java will always execute the main method first. It's going to create age and set it to 5, then create other and set it to 15. Then it's going to call change on variable age. Now, whenever there's a method call, that means we can't be in the main stack frame anymore. We need a new stack frame because we have a new method. Okay, so where we had main, we're now going to have another stack frame for change. Okay, is everyone happy with that? We've now got a new stack frame for change, and it's going to have the variable age because that's what was passed in, and it's going to have a copy of the variable that was sent in. So because I called it with variable age, that value 5 is going to get set here. So this variable age also has the value 5. Sorry, I've got a bit of a flu, so bear with me. The interesting thing here that I want to just point out is that although these variables are both called age, you'll notice that this variable age is local to this method and this variable age is local to this method. So they are two variables that just have the same name, but they're in no way the same variable. You've got one age variable in the main stack frame which has value 5, and one variable in the change stack frame which has value 5. Okay, and it has value 5 because it was copied from this age variable, because that's what was sent in. Then inside the method, we say age equals 9. Right now that's happening inside the change method. So that means it's going to go to the change, it's going to go to the age variable in the change stack frame and change its value to 9. But notice that the original age variable hasn't changed. Okay, so in the sort of C++ parlance, you're doing something like a pass by value. Right, so basically you copied the age variable, which means when you make any changes to the variable, you're making changes to the copy, not to the original. Which means that then when you return from the method, your age variable is unchanged, and when you call system.out.println on age, you get 5, not 9, despite the fact that age changed to 9, because we actually changed a copy that also happened to be called age. Okay, everyone happy with that? Now, sheesh, out of habit I say things like, is everyone happy with that? And then to be fair, I get the same response I get when lectures are in person, meaning no one says anything. But I'm going to assume everyone's happy with that then. Now in C, you could have made an int star here, and so you could have passed in a pointer. In Java, you can't do that, right? it will always, an integer will always be passed by value. You can't tell it to pass by reference. There's just, it's not available. Okay, now the next thing is what happens with objects. Remember we said that objects are created in the heap and references are stored in the stack. So let's look at something like this. I've now got a class called person, which just has an age variable which is set to 0. And in my main method, I then say person p equals new person. What that's going to do is it's going to create a new person because of this side of the operator, the new person part. So I'm going to get a person object sitting in the heap somewhere. And that person object is going to have an age variable whose value is 0. Okay. Now let's say that object is in memory address 15db9742, utterly randomly. Then when I say person p equals new person, that's going to create a local variable p in the stack, which has that memory address as its value, right? So you can see that p is fundamentally a reference or a pointer to this person object. Okay, so when I create objects, it's important that the objects are not actually stored in the stack. They're stored in the heap, and the stack frame just has a pointer to the object. Okay. Okay. Then I call p.age equals 15. Now what happens then is that Java will say, well, p refers to this object. So from this .age, it means I need to go look for the age variable inside this object, and I need to set its value to 15. So if I then system.out.println p.age, it's going to go to p, and then the .age takes it to the actual object. So because of the memory address, it's going to go there, look for the age variable, and print it out. And so it's going to print out 15. Okay, so objects also kind of work as you'd expect, but they're always stored as references, right? They never store, you don't store an object directly on the stack. Sorry. Okay, now here's an interesting thing. Let's say our object, our person object, instead of just having an age, it also had a name, which is a string. Now string, you can see, starts with a capital letter. It has a capital S. So it is itself a class. And variables of type string, like name, are objects. They're not primitives. So then what's interesting about that is when I say person p equals new person, what that's going to do is it's going to create an object with age 0 and name null because the value name was not set. So that means it's created a sort of identifier name inside the person object, but it doesn't have any value. Okay. When I say p.name equals Pravesh, now you may be thinking that means I just put Pravesh in here. Well, I don't, because Pravesh is itself an object, right? It's I am not an object. I am a person. I am a human being with feelings, and yeah. Anyway, the Pravesh itself is an object, so that means it gets created somewhere in the heap, because objects get created in the heap. Let's say it gets created at position 102 EB9716, yet again completely randomly. Then what that'll mean is that name, p.name equals Pravesh, p will follow into name, and that null will change to the memory address of the object. So even in the heap, when I have objects inside an object, they're stored as references, right? They're not stored directly inside that object. You just get a pointer to where the actual object is. Okay. When I say system.out.println p.age, I'm just going to get 15 as normal because I didn't change anything there. Okay, but now let's see what happens when we send an object to a method. Now, this is an interesting one. Here, behavior changes a little bit, so pay attention a bit here, I think. So, okay, so what I'm going to do now is, previously I had this change function which took an int, which was a primitive, right? Now, I'm changing my change function to take a person. And then all I do is I set that person's age to 9. Okay, so in my main method, I create the person p as normal. I set p.name equals Pravesh, p.age equals 15. So I've got all of this set up. I then call change on p. When I call change, remember that means that I'm calling a method, so I get a new stack frame. That new stack frame will have the variable I, and I will be a copy of p because p is the parameter that was passed in as I, right? So I is just a copy of p. In my change method, I then say I.age equals 9. What Java is going to do is it's going to look at I and follow the pointer to this object and set the age value to 9. Okay, and when I system.out, okay, and then I'm going to return to the main method, so my stack frame disappears. And when I print out the age variable, I now get 9. So that was interesting. Now the variable changed, right? So remember over here, when I was doing this with primitives, when I changed the variable inside the method, I ended up changing the copy. So it didn't, when I printed out, it wasn't changed, right? But here, even though I did almost the same thing, the variable did change. And the reason it changed is because although I is a copy of P, they're both references to the same object, which means if I change I's age property, I'm automatically changing P's age property, right? So this becomes more similar to pass by reference in C or C++. In effect, what I did was, though, I actually passed by value, but what I passed by value was a reference. I know that sounds a bit weird, but you can sort of treat it as if it's passed by reference, even though I passed a reference by value, if that makes sense. But so that means if I want the value to change, in C++ I would have passed in a pointer. Now I can't. I have to wrap the variable in an object and send the object in, because objects are sent by reference. So I don't get to choose whether I want to send a variable by value or by reference like I could in C or C++, but I do get to choose whether what I'm sending in is an object or a primitive. And if it's a primitive, it'll get passed by value, and if it's an object, it'll get passed by reference. So in essence, I have sort of the same degree of control. Okay. Now, let's look at how strings work. Strings are interesting ones. So let's say now what I did with my change method is, instead of saying I.age equals 19, I said I.name equals Steve. Okay, because who wouldn't want to be Steve? So now I've got my variables set up as normal, and then I call change on P. So when I call change, that means I get a new stack frame, and I is a copy of P. Okay. Now when I say I.name equals Steve, you may think that I can just change this string to Steve. But in Java, strings are immutable. They cannot be changed. Okay. One of the reasons they can't be changed is because memory has been allocated, and the right amount of memory has been allocated. So let's say I said, I mean, it was Pravesh. Let's say I said I.name equals Pravesh is really cool. Then that would be a longer string, and potentially I don't have enough space to put that here, right? So strings are immutable. You can't change them. So how Java will handle this I.name equals Steve is it'll make a new string with the value Steve and put it in memory, right? So that one that had the value Pravesh is still there. I didn't change it. I've got a new string with the value Steve, and let's say it randomly was in 2041C4318. That's, I don't know, some random memory address. Then the fact that I said I.name equals Steve means Java is going to follow the I pointer and change the name variable to that memory address, right? So the memory address will become 2041C4318. Does that make sense? I did it again. So then when we return, the stack frame disappears. But if I print out p.name, I now follow p to here, and I follow the name pointer to Steve. So p.name will now print out Steve. Okay. But now what happens to this Pravesh? It's sort of just sitting there doing nothing, which is what Praveshers like to do the most. So that that Pravesh variable is sitting there doing nothing, and that means what's going to happen is the garbage collector is going to decide that variable is garbage. I didn't think this through, but anyway, it's going to decide Pravesh is garbage, and so what it's going to do is It's going to mark it for deletion because there is no way to get to this Pravesh variable. There's no reference to it anymore. The only reference there used to be to it was in this object, and that's been reassigned to Steve. So that means the garbage collector is going to delete Pravesh. I hope there were a lot of ahs there in the from all of you watching. But anyway, Pravesh got deleted, and the when we printed out p.name, it was printed out Steve, right? Because p follows follows to name. So the garbage collector sort of kicks in whenever stuff happens there. But the important thing here was that strings are immutable. They can't be changed. So if at any point I change a string, what Java will do in the background is just create a new string. Okay. Now that immutability also has other interesting effects when it comes to our method calls and referencing semantics. So look at this code. This code creates a string called p, which is equal to Pravesh, and I then call change on p. Now remember, p is a string, which means it's an object, which means I'm passing it by reference, right? And then I say I equals Steve, which means I'm changing the value. Now because I'm passing it by reference, you may think, well, changes that happen in here will change the original, and when I print out here, I'll get Steve. But let's see what actually happens. So I set string p equals Pravesh, so I ended up with this string object here with value Pravesh, and there's a pointer to it called p. When I call change on p, I get a new stack frame. I get this variable I, which is a copy of p. When I say I equals Steve, then well, it's not possible for me to change this variable Pravesh. It's immutable. So that means I have to make a new variable called Steve. And if that variable is in position A429368, some random string again, then that's what I changes to. But if you look at it, P didn't change at all, right? So this is important. The fact that strings were immutable meant that even though P and I were pointing to the same place, changing I didn't change P. All it did was redirect I to a new object. Okay? So that means now when I come back, if I follow P and print out P, it's going to print Pravesh, right? Which is exactly the opposite of what happened the last time, right? Because the last time I got Steve, and it's hard to come up with a sort of shorthand for why that happened. It's very important to understand how Java memory works, and then these things are predictable. You're like, okay, that's going to print out Pravesh. I know that because, like, although I sent in a copy of the reference, that copy will have gotten redirected, but the original didn't, right? Feel free to watch this lecture many times if that was an unpleasant sentence. It sounded like an unpleasant sentence to me. But yes, so basically, because of immutability, that didn't change. Now here, Steve then has no references to it because that stack frame got removed. And so this time Steve is garbage. I got you this time, Steve. And so Steve gets deleted by the garbage collector. Goodbye, Steve. Okay. Now, another interesting thing is the double equals operator, right? You guys know what it does. It does comparison. Interestingly, what it does is comparisons of variables on the stack, particularly on the stack. So let's look at this code. If I say int age equals 5, int other equals 5, and then system.out.println age equals other, I'm comparing the two values because primitives are stored as values, and 5 is equal to 5, so I get true. But let's say I had two complex types. Let's say two strings. I have one variable on the heap which has a value Pravesh, and another variable on the heap which also has variable Pravesh. There's some code that could generate that over here to get two separate variables with the same value. P points to this memory address and Q points to this memory address, but they have the same value, right? So if you were to print out P double equals Q, so basically printing out whether P is equal to Q, you would potentially expect P to be equal to Q, right? You'd be saying, well, they both have the value Pravesh, so they're equal. right? I have string q equals Pravesh, string p equals Pravesh, and string q equals Pravesh.2 lowercase, but it's already lowercase. So p and q are the same, right? So if I say p equals q, I should get true, but I don't, I get false. And the reason I get false is because the equals operator is comparing on the stack. And if I look at the values of p and q, they're not the same. They're not the same because they're actually different references. Okay? So when I do use the double equal to operator on objects, I'm comparing the references, meaning I'm checking whether the two are actually the same object in memory. And that's very rarely what I want. I don't generally want to check if, well, okay, it depends on your use case. Sometimes you want to check if two things are the same object. But most commonly when I use this operator, I want to check if the values are equal, right? So how you do that with objects is you use the double equals. You use the dot equals operator. So if you look at this code here, it now says system.out.println p dot equals q. Okay, and that'll give me true because the dot equals operator will go and look inside the object to see whether they're actually equal. If you're making your own objects, you have to define this equals operator in your object so that the dot equals operator knows how to deal with the object. So the people who wrote the string class would have written an equals operator that returns true if the value arrays are equal. Okay, so I hope that that makes a bit of sense. Again, all of this stuff, it comes up when you're coding. You know, this is not weird knowledge that has no reason to be in your curriculum. The reason it's there is because this is going to happen to you. You are going to say p equals q, and you're going to happily code away, and your results are all going to be wrong, and it's going to be because you should actually use dot equals, right? Similarly, you're going to pass objects into methods and not understand why the value changed or didn't change, and the only way you'll know is by having a grip on this, or at least understanding that this is the thing you need to look up. Okay, so I hope that was a fun and interesting lecture. I don't think it was ridiculously long. I hope it was reasonably understandable. And I hope you guys actually take a look at the fire thing on Moodle. I don't know if you guys have seen that. I'll just talk about that very quickly if I can figure out how to get Chrome to show up in here. Give me a minute. So the fire exercise is one of the lab items that I added for you guys on Moodle. Okay, so this is the exercise for the sort of smoke / fire thing. I'm just going to show you what the animation looks like. So if you look at it, it kind of looks like a fire, right? It kind of looks like there's a fire happening there, which is you know, it's sort of cool looking, I think. But what's really cool about this, I think, is that it's all done with some very simple kind of math. There's not much code in a program that does a fire demo. So this used to be quite a popular thing to do, is these little demos of fundamentally math doing cool looking things. But basically, what's really interesting about how the fire demo works is if you view the thing, you can see that at the bottom of it, now to make that line at the bottom disappear, well, let's see. Maybe, I don't know, who knows. Okay, but anyway, at the bottom of it, when you sort of look behind this okay, I don't know if that's visible. Okay, let's try this again. Okay, so this bottom line, right? This is an interesting one. This bottom line is just random pixels, right? If you pictured this as black and white, this bottom line is just a list of utterly random values. Okay, so we set the bottom line to random intensities. Then For the line above it, we set its value to the average of the values of the three values below it and itself. Okay, so basically the pixel above it has some value. We take that value and we average it with the three below it, and then we set that to its value. And we just do that in a double for loop for literally the entire set, right? And that's the entire algorithm. When we run that algorithm, it ends up looking like fire. So basically that randomness, when it gets averaged, it sort of propagates upwards in a very interesting way and kind of looks like fire. So normally when people display this, they won't draw that bottom line so that you don't realize there's some randomness going on at the bottom there. But I thought that was kind of cool. So in the smoke lab, there's a very short bit of code that you can do to play with this, and yeah, I think it's quite fun, and you can mess with it. You can kind of make the fire green and stuff. I'd like you guys to try that as well. Okay, I think that's pretty much everything I wanted to talk about today. I hope you all have fun programming in the next week, and pretty soon we'll get onto the Android stuff, and it's gonna be a lot of fun. Thanks for listening to me.